and play. And a happy Tuesday evening. Here we are once again. Ham radio class, the amateur extra, going to achieve the top level amateur radio license in the United States. I'm your instructor this evening, Gary, ham radio call sign Whiskey 4 Echo Echo Yankee, and we're going to be covering Chapter 7 in this book. This is the book that we use, the American Radio Relay League License Manual for the Extra Class, the 13th edition. This is the one you want. This has the most recent question pool. And so tonight, you know, we're actually probably over halfway through the class, so kudos to y'all. I've gotten some emails from some folks that have already tested and passed. Yay. You don't that's not a pressure on you. Just keep going at our usual pace and we'll get you there so that you'll get your upgrade to amateur extra class. So that's the whole point of this. Tonight, Chapter 7, Radio Measurements and Performance. And go ahead back to the laptop, please. And we'll get started, though, with a little what I call waveform review. This is not in the book. This is not a section, but I want to just kind of review some stuff. So here we have a graph. Let me turn on my laser pointer. Oops, gotta find my, there we go. So here we have a graph with amplitude on the vertical scale and time on the horizontal scale. So this is what we would call a time domain view of DC. It's at a constant voltage over time. So that's a direct current in this case, and direct DC voltage. It's about 250 volts or thereabouts over time. AC alternates between positive going voltage and negative going voltage. So you can see here we start the zero line, go positive, zero line again, go negative. You've seen all this before. This is just review. This is basic. Again, here we are in the time domain. And this sine wave that we're looking at can be generated electronically, or it can be generated rotationally through a generator or other mechanical means. And this is a single frequency. Same kind of animation here. Looks here. You can see the relationship between the circle and the sine wave. We sometimes talk about 0, 90 degrees, 180 degrees, 270 degrees. That's what this is all talking about here. And so let's go down to my workshop and let's take a look at a sine wave. And this is where we'll have some audio from the laptop, Bruce. So here we are in the workshop. This is our first test setup. We have the generator, which is right here on the left-hand side, set up for a 500 kilohertz sine wave, and it is feeding both my oscilloscope, you can see the sine wave, and the spectrum analyzer. And you can see on the spectrum analyzer the left-handmost blip going up there with the marker. That's the primary signal for the sine wave. And any harmonics, which are indicated by the subsequent markers, are very down, 60 dB below that carrier level. So a sine wave is essentially a single frequency output. And so what you're seeing there is in the frequency domain. You're looking amplitude on the vertical scale and frequency on the horizontal. And if you look very closely, you'll see that I misspoke, and the other harmonics are about 40 dB down from the fundamental on the tiny spectrum analyzer ultra. That's the device that's being used here. With sine wave measurements, we talk about amplitude, we talk about the frequency, and we talk about the period. The period is the time in seconds or milliseconds or microseconds it takes to complete one complete cycle. So again, here we are in the time domain. And by knowing the period and that the wave travels at the speed of light, a radio wave, well, we can calculate a radio wave's wavelength by using that timing, that milliseconds or microseconds or whatever it is, and knowing that the speed of light travels at 300 million meters per second, we can give you the wavelength in meters, for example. And we have peak-to-peak values, measuring from the positive going peak to the negative going peak. That's the peak-to-peak value. Whereas if we just use one of those, that's the peak value of AC voltage on a sine wave. So again, peak-to-peak, peak. Now another one is RMS, or root mean squared voltage. It's 0.707 times the peak voltage with a sine wave. And RMS has to do with heating. It's the amount of power that is contained to heat something up to a particular temperature. You can compare it to if you had a DC voltage and then an AC voltage. If the RMS voltage is equal to the DC voltage, the heating effect is the same. And here's the long definition, but the neat thing about it is that with using RMS, you can measure the power of a non-sinusoidal waveform. So we've been talking about sine waves here, but sometimes you have complex waveforms that you want to measure the output power, the power, and so RMS measurements are the way to go. And as we said, it's if you had a DC voltage from a battery here connected to a resistor, and you measured the temperature, okay, that's the reference voltage, and then you have an AC voltage that heats the resistor to the same temperature. That would be the same RMS equivalent. That's the heating effect. Well, Gary, why would I want to do that? Why is that important? Well, I was blessed with a 20-year career with the Voice of America, and there we used very high power broadcast transmitters. 500,000 watt shortwave transmitters. Here's a Marconi, for example. And if we wanted to know, is this transmitter actually putting out its rated power? And we've got meters and we've got measurements, but the best way to do it was actually to run the RF energy through a transmission line. Look at the size of that transmission line. Compare it to RG8X, for example, going down to a load that is liquid cooled. And we would measure the temperature of the slurry that is being used to cool the resistor, the non-inductive load, and by knowing the temperature rise and knowing the flow rate of the coolant, we could calculate accurately the actual RF output power of a modulated signal, say for example, from a 500,000 watt transmitter. So that's a dummy load. Somebody asked me, what the heck is a dummy load? Well, this is a really big one. At your home station, more like this is what you're going to find if you go to Hamfest. This is the original Heathkit Can-Tenna, which is a 50 ohm non-inductive, non-reactive resistor in a paint can, essentially, with mineral oil around it, which provides the cooling medium for here. And now this will do 1,000 watts for sure, 1,500 watts for a brief period of time. This is a dummy load, a test antenna. To complete our definitions, although it's not on the test, the average voltage is 0.636 times the peak, and it represents the area underneath the curve. All right, what's better than one sine wave? Well, two sine waves that are in quadrature, or 90 degrees out of phase. These are called I and Q signals. I in phase, Q quadrature, and you'll see these being used in amateur radio, both in modulation and in demodulation. Other waveforms are the square wave, triangle wave, and sawtooth waves. These are all again in the time domain, and these more interesting, more complex waves are actually made up of other sine waves, and we know this because of Fourier analysis. Fourier analysis proves that complex waveforms are made up of various multiples of sine waves. And so the square wave, for example, is made up of a sine wave at a fundamental frequency plus the odd harmonics in different power relationships. And you can see here in this animation, we start out with the fundamental at the top, and then here's the third harmonic. Here's the fifth harmonic. Here's the 7th harmonic, and when they start adding together, I love the wheels within the wheels within the wheels, you see that the wave starts squaring up. Typically, we say a really good square wave with right angles, it has at least 10 harmonics that have been built up. Let's go back to the workshop and take a look and see what I could measure.
Next up, we set the generator to a square wave output. And you can see over on the oscilloscope here, yes indeed, it is a square wave. And if we look at the tiny spectrum analyzer, you can see that the primary outputs are the odd harmonics.
So that's a square wave. Triangle waves also have odd harmonics, but their distribution is slightly different. And you can see here on this graph the harmonics that make up a triangle wave, and we're able to reproduce it down in the workshop.
Now we set the generator to output a 500 kilohertz triangle wave. And if we pan over to the oscilloscope, you can see indeed it is a triangle wave. And if we look to the tiny spectrum analyzer, you can see that it has odd harmonics as the main components.
So triangle wave and square wave are odd harmonics. A sawtooth wave uses all of the harmonics, the even and the odd numbered harmonics. And you can see here on this animation as it builds up, it builds toward the triangle wave. And once again, the workshop is here.
And now we have the generator set to output a sawtooth wave. And you can see what it looks like in the time domain on the oscilloscope. And on the tiny spectrum analyzer, we can see that its components are the fundamental plus all of the harmonics.
So you can come back to me just for a second, Bruce. So some of this information you used to have to know for the extra class licensing test. It's actually, the test has been updated with a new question pool, and I think it's made it a little easier, but I didn't want you to be shortchanged. I wanted you to see these things so that it makes more sense to you when you read about it in the book. So we have those various waveforms. We also have, as I mentioned with the radio transmitter, more complex signals, modulated signals. Here we have in the time domain an audio signal on the top, high frequency radio carrier, amplitude modulated signals. This is the envelope in the time domain, or frequency modulated signals where the amplitude stays 100%, but the frequency is modified. And transmitter output with an unmodulated sine wave is called the average power. And you can calculate the power with the RMS values for voltage and current. Now, with modulated signals, this is unmodulated signals, with modulated signals, what we do is we look at the peak value of the voltage. And so to calculate peak envelope power, we find whatever the peak level is, whatever that value is, and we multiply that by 0.707 to give us the RMS value. The PEP value up here is typically 2.5 times the average or unmodulated carrier. So this is something you might want to know. And voice processing is what increases average power of a modulated signal. It is the characteristics of the modulating signal that determines the average power output from a single sideband transmitter or an AM transmitter, for example. And to measure peak envelope power, we use the peak envelope voltage, and then this formula here, the peak envelope voltage taken to RMS, square it, and then divide it by the impedance, which typically is 50 ohms. All right, that was all waveform review, not on the test, but as background information for us to get started. All right, test equipment, we're going to breeze through this. This could easily be a semester-long course in college, but know about, for example, with multimeters, no matter whether you have a meter that is analog or digital, there are three things that I want you to consider. The accuracy of the meter. Has the meter been calibrated to a standard so that it's traceable? You know, okay, this is a very accurate meter. Is it precise? Can you look on markings on a scale and say, okay, yeah, I can see the difference? Or are there a number of digital readouts so you can see the difference? And then the resolution, that's the smallest difference that can be accurately distinguished. Now, this is not sponsored. I bought this on my own, but this is a neat little thing called a digital voltmeter calibrator. And it provides a standard in a box. I have one over here on the calculator cam, so you can see the size-wise, it's not all that big. But you can use this. It has voltage standards for AC and DC. It has resistance standards, so it allows you to make sure that your digital voltmeter is accurate. So I've used it on all of mine. Here's the background information. I don't remember what the price is on these guys. But if you use your multimeter regularly, whether it be an analog, a Simpson 260, or a digital meter, that you need to know some things about multimeters. Let's go back down to the workshop.
I wanted to demonstrate the difference between an RMS measuring AC voltmeter and a non-RMS meter. And we can do that using my digital multimeter calibrator here. And at the moment, the calibrator is connected up to my oscilloscope, which, if we look closely, it's a square wave, and it's a plus 5 volts and minus 5 volts with a 50% duty cycle. And the equivalent DC of that would be 5 volts on all the time. So now I've turned the lights on so you can see the meters a little better. This is my Beckman digital voltmeter from about the 1990s. And on the AC scale, you can see it's reading 5.4 volts AC. And now in contrast, I've hooked up my newer Chinese true RMS meter, and you notice that it is reading 4.969 volts, and you can maybe read the frequency readout above 99 hertz. This is more accurate.
And actually, both meters are working exactly as designed. The first one that was reading 5.4 is not a true RMS meter, whereas this newer one is. So if that's important to you, keep in mind that these differences do exist. All right, here we're going to go a little philosophical. The observer effect. The act of observing something will influence the phenomenon being observed. Well, how does this relate to electronics? Well, it has to do with multimeters, especially older multimeters, and their effect on a circuit. They actually provide their own resistance to the circuit when measuring voltage in this case. And depending on how the multimeter is designed, it can actually change the voltage across the component that you're trying to measure. So old analog meters were rated in ohms per volt. Typically, a multimeter would be 20,000 ohms per volt. And this refers to the meter full scale reading times its ohms per volt rating is that device's input impedance. So on a 10 volt scale, the meter input impedance would be 200,000 ohms. In a solid state circuit, that's not very bad, but in a tube type circuit, that could really change things all around. It's all about how much does the meter load down the circuit under test. And here, for example, is a 20,000 ohm per volt schematic here with just a basic 50 microamp meter full scale. It has a 5,000 ohm internal resistance. And on the 1 volt scale, they add a series resistor of 15,000 ohms. So 15,000 in series with 5,000, 20,000 ohms per volt. That's what they're talking about here. And let's go back down to the workshop, and I'm going to measure one of my smaller meters.
I want to demonstrate the concept of ohms per volt using this small snap-it analog meter. It's set on the DC volts and 2.5 volt scale. This little meter is rated at 10,000 ohms per volt. So 2.5 times 10,000 actually gives you a loading of 25,000 ohms as measured on my meter here to the right. We're actually connected from positive to positive, negative to negative, and reading the resistors inside the meter. 25,000 ohms would load down a circuit considerably, so this is something that a technician has to keep in mind. If we go to the 50 volt scale on the little snap-it meter, 50 times 10,000 is 500,000 or 0.5 mega ohms as indicated on the digital meter. And if we go up to the 250 volt scale, it's 2.5 mega ohms. So this is a meter with 10,000 ohms per volt. A lot of meters that were sold with 20,000 ohms per volt or 30,000 ohms per volt, they would load the circuit less. But the best is a vacuum tube voltmeter or modern digital voltmeters, which have a 1 mega ohm or greater input impedance that does not load the circuit down.
So that's important to know, and in fact, if you got service literature from Howard Sams or somebody like that back in the day, they would have voltages written on the schematic, and it would tell you what meter that they used in order to make that measurement. And if we go over to the calculator cam, here's a Radio Shack multimeter, and notice that it's rated at 20,000 ohms per volt on DC, and 10,000 ohms per volt on AC. So just keep in mind that this is a common specification for analog and digital multimeters. And I mentioned vacuum tube voltmeters. You'll see these at Hamfest as well. Here's an older night kit. I built one of these back in the day. This unit has a 11 mega ohm input impedance with the probe that comes with it, and this will not load the circuit down as much. But the thing is that if you're reading voltages off the schematic that were taken with a 20,000 ohm per voltmeter, the voltages read by this might actually be higher than are listed on the schematic. You always got to keep this stuff in mind. All right. Other stuff, and we're just going to casually go through this, they're not covered anymore, but grid dip meters that are used to find the resonant frequency of an LC circuit. So here's an old Millen grid dip meter. You plug out one of the coils that you see here into the top of the meter up here and bring it close to a resonant circuit. It's called being loosely coupled. Too tightly coupled gives you an inaccurate reading, but you'll actually see a dip on the meter when you adjust this to the frequency that corresponds to the resonance of LC circuit, a resonant circuit. You can also use component impedance bridges to find out information about an inductor or a capacitor or a resistor. You put the unknown device across some terminals and then adjust the knobs, and you'll get a very precise null on the meter. You'll also see these at Hamfests. Mostly digital meters have replaced all of this, but I just want you to know about them. RF circuit bridges are also another way where you can actually input a radio frequency signal from an RF generator into a bridge circuit, put your unknown here. The unknown could be a component or it could be an antenna, and get a null indication here when you adjust the corresponding variable elements in the bridge, and that will give you information about the circuit that you're trying to test. This uses the RF generator as a single frequency source. You also have noise bridges, which use wideband noise as a signal source, and you use a receiver, a single frequency receiver, as the detector. And by doing that, you can adjust the bridge for a null, and that will then also tell you the component values, the R or the X values of what you're trying to test. As I say, most of this has been replaced by digital LCR meters or other things that are built into DVMs. The bridges that we used to use for antennas have been largely replaced with antenna analyzers. Here's the MFJ 259, which is a classic analyzer that'll give you a lot of information about an antenna that you're adjusting, for example, or the Rig Expert. This is the AA54. This is the one that I use all the time. And the nice thing about some of these, like the Rig Expert, is that you can actually use software connected to the analyzer via USB and get Smith charts or plots to see what your VSWR is versus frequency. A lot of things now that we have available to us back in the day were not available to hams. They had to use all of those more manual means. Something you don't see so much anymore, but used to be a hot item, were frequency counters, because people were very concerned about being on frequency, especially if you had a variable frequency oscillator that tended to drift. You wanted to make sure that it was in calibration, so this is the thing that could help you to do that. And frequency counters, you pay for the time base accuracy. So frequency counter that has a very iffy time-based accuracy is cheaper than a lab-grade instrument. So that's what you're paying for. Also stability in parts per million. Again, the input impedance on these are pretty high, typically around 1 megaohm. And on a lot of these frequency counters, then there's also a button down below here called period, which instead of measuring the frequency of a signal, it will, especially for low frequency signals, it'll measure the period of one complete cycle in milliseconds or microseconds. So period measurement can sometimes be important for you as well. Frequency counters are rated up to a certain frequency above which they're not going to be accurate. If you need to measure a frequency above that, then you can buy prescalers. Prescalers are put in between the signal that you want to measure and the frequency counter, and it is a divide-by device. It'll typically divide the frequency by a factor of 10. So it increases a counter's frequency range by the same amount. All right, come back to me just for a second. Back in the day, oscilloscopes just fascinated me. What is going on with this line going across this green screen? And oh my gosh, back in the day, the tube type oscilloscopes were what we called free running scopes, that you would actually have a horizontal knob that would adjust the sweep rate of that signal, and they'd run all the time, and maybe you could get them to lock in on synchronizing pulses from a TV signal or things like that. So that's an old analog oscilloscope. Well, nowadays, even analog oscilloscopes and now digital oscilloscopes have much more sophisticated ways to control that horizontal trace. Come on back just for a second. On the left here we have an analog oscilloscope, but it's a triggered sweep scope. And on the right is a Rigel a digital oscilloscope. I've got one of those down in my workshop down below. Old oscilloscopes or new oscilloscopes, they measure amplitude versus time. So we're viewing waveforms in the time domain, and they have various controls. As I mentioned, on the old ones, it was just the horizontal sweep rate, but now we've got time base per division. So each one of the graticule marks on the display represents a certain period of time. And also you can control when the trace starts, known as triggering. And there's also then focus, intensity, and position. But we can say that an oscilloscope displays amplitude at different times. That's their definition, not mine, but know about that. Okay, triggering. On most now modern scopes, whether they be analog or digital, this is the kind of thing that you will see, this triggering panel, where you can actually start the sweep from left to right at a certain voltage level on a signal. And it could be from the A channel, here's the A channel, or it could be from the B channel, here's the B channel. It could be from an external input, a triggering input, okay? And it can also be something called the line input. See the line right here? And what that is referring to is the power line. It's synchronized to the power line. So if you're making measurements on things that are using AC power, this might be the most stable way to trigger. Example, if you're looking at a power supply and you're trying to measure power supply ripple, you might want to have the scope triggering on line frequency, and that would then lock this so then you'd be able to see the ripple coming into the filter section of your power supply more easily. Now, when you're using an oscilloscope is no good unless you've got a probe to match. Oscilloscope probes are designed and they have certain frequency limitations like the oscilloscopes do, so you want to match the scope's input impedance. Typically they're ×10 probes. They have a 10 mega ohm resistor built inside. They're low capacitance and they have a ground lead. See, this is the ground lead, which is going to clip into a little position right about here. And notice how short it is. That's on purpose. You want to keep the ground lead as short as possible to minimize noise pickup on an oscilloscope. If you add an extra alligator clip lead or whatnot, you may get some erroneous noise readings. So you want to make sure that the probe ground lead is as short as possible. And these probes, especially in the ×10 position, they can be compensated so that their frequency response is flat. And the scopes provide a way to do that built in. What you do is you connect the probe to a calibration point on the oscilloscope, and then you use a little tool and you adjust the calibrated output square wave for flatness. Well, let's go take a look. So I want to talk through the process of probe compensation on an oscilloscope. Here I have my Rigel oscilloscope on, and the probe is connected to a calibration output here in the right corner. And you can see the square wave on the screen, and you can also see that the square wave leading edge is peaked. That's not what it's supposed to look like. It's supposed to be a square wave. The probe is in the ×10 position. You can only make this adjustment when it's in the ×10 position. And you have a little tool that scope manufacturers send you, or you can use a little alignment tool. It's just a small piece of metal held in a plastic holder so you don't get too much stray capacitance down near the control. And by adjusting the variable capacitor that's on the scope probe, see there it's squared up. If I go too far, you'll see the leading edge becomes rounded. That's no good either. So you want to adjust it until your square wave is square. So all oscilloscopes will have that capability, whether they be analog or digital, in order to make sure the probe compensation is set properly. For digital oscilloscopes, you'll also have to keep in mind that we talked about the Nyquist theorem, where sampling rate has to be at least 2 times the highest frequency that you want to measure. Well, sample rate is critical. It determines the scope's bandwidth. And if the sample rate of the scope is too low, it'll give you false signals, known as aliases. It'll look like you're measuring something, but it's not a good signal. And one nice thing about digital oscilloscopes, you can write the waveform to memory and then call it back later for later analysis, and you can manipulate the screen around. So digital scopes are very nice. They have automatic frequency and amplitude digital readout. I mentioned that you can store the waveforms, and then you can also manipulate the time base on a captured waveform to look closer in. So if you'd like to play with an oscilloscope, a real working oscilloscope, you need look no farther than your Windows-based computer. Here's a sound card oscilloscope, and we are actually using this very software here in the studio tonight to monitor our microphone signals. This is using your audio card built into your computer, which is probably sampling at 44 kilohertz or 48 kilohertz are typical. So it's only good for audio signals. Again, the audio card sample rate determines the audioscope's bandwidth here, but this is software, so the sound card sample must be at least 2 times the highest frequency, but we use it here. There's an XY position. We use it here as a vector scope to tell us to make sure that our audio signals, like from my microphone, is in phase, because we had some problems earlier on where we had kind of fuzzy audio. That was the problem, and this tool allowed us to check it out. So the URL here is down at the bottom. It's free. It is shareware, though. If you use it on a regular basis like we do, we paid for it just to give the guy some money. So that's a sound card oscilloscope. You can play with all of this. And finally, a logic analyzer. It's a device that displays multiple digital signal states simultaneously. This is from back in the day when you were designing digital circuits with gates, AND gates, OR gates, NAND gates, NOR gates, exclusive ORs and whatnot, and you wanted to see the timing of signals reaching the gates and how they were activating. And so a logic analyzer might have 16 or 32 or 64 inputs, usually on cables coming off the back of it, and you can display all these various signals and their timing all at the same time. That's a logic analyzer, kind of a specialized form of an oscilloscope. So far we've been looking in the time domain, but if we want to look in the frequency domain, then we're talking about a spectrum analyzer. And a spectrum analyzer has amplitude on the vertical scale and frequency on the horizontal scale. It can display a signal's bandwidth, for example. It can display distortion products. Generally, they're very well calibrated and filtered. I saw one of these actually at the recent Stone Mountain Ham Fest for about $1,000, which is about the lowest price I've seen on one of these. New, these were about $20,000 to $30,000. So with any spectrum analyzer, here's the input to it. It's an end connector. You need to keep your input signal down below the maximum, and it's right there printed on it in yellow. The maximum signal level that you can bring in there, but probably about plus 6 dBm. And you need to watch your input level and attenuate any RF signals. You can't run a transmitter directly into a spectrum analyzer. What you have to do is you have to get something like this, which is a high-powered RF attenuator, which will drop the power coming from a transmitter, for example, down to a level that the spectrum analyzer can use, and also then absorb the radio frequency energy here in this dummy load, this test antenna, essentially. And spectrum analyzers are used in conjunction with something called the two-tone test. It's when you modulate a transmitter, audio transmitter, with 2 non-harmonically related audio tones. So 1,000 cycles and 1.5 thousand cycles would be fine, but 1,000 cycles and 2,000 cycles, that'd be no good. Those are harmonically related. And what you're doing then is measuring intermodulation distortion and the resulting products on a spectrum analyzer on a display, something like this. Now, for most folks, I still can't afford that $1,000 spectrum analyzer, but I could afford this. We saw this earlier in the day. This is the tiny Spectrum Analyzer Ultra, available on Amazon and other sources. A really handy and nifty device. It does not have the resolution to be used for a two-tone test, but it does have a lot of special features. We'll talk more about it in maybe in the antenna chapter as well. All right, we made it through the first section. Let's answer some questions, and then we can take a break. So which of the following limits the highest frequency signal that can be accurately displayed on a digital oscilloscope?
A.
I heard an A. Do we concur? Yeah, the sampling rate of the analog to digital converter. It's got to be at least twice that of the highest frequency that you want to measure. And which of the following parameters does a spectrum analyzer display on the vertical and horizontal axes?
Bravo.
Yes, signal amplitude on the vertical and frequency on the horizontal. And which of the following test instruments are used to display spurious signals and or intermodulation distortion products generated by an SSB transmitter?
Bravo.
Yeah, that would be the spectrum analyzer. And how is compensation of an oscilloscope probe performed?
Alpha. Alpha.
Yeah, that's what we did. The square wave is displayed, and the probe is adjusted until the horizontal portions are as nearly as flat as possible. And what is the purpose of using a prescaler with a frequency counter?
Delta.
Delta, yeah. If you've got a 500 megahertz frequency counter, which was typical back in the day, and you wanted to measure a 1 gigahertz signal, well, you had to put a prescaler in between to reduce the signal frequency to within the counter's operating range. That's a prescaler. And what is the effect of aliasing on a digital oscilloscope when displaying a waveform?
Alpha.
That's what you're going to get. You're going to get a false, a jittery, it's a low frequency version of the waveform, as Dave showed us earlier. It doesn't look anything like the waveform is supposed to look like. It's an alias. So which of the following is good practice when using an oscilloscope probe?
Alpha.
You want to keep that ground connection as short as possible so you don't have noise pickup. And which trigger mode is most effective when using an oscilloscope to measure a linear power supply's output ripple?
Delta.
You want to use the line triggering. Yeah. And which of the following factors most affects the accuracy of a frequency counter?
Bravo.
It's the time-based accuracy. That's what you're paying for. It's measured in parts per million. And what is the significance of a voltmeter's sensitivity expressed in ohms per volt?
A.
A is correct. The full scale reading of the voltmeter multiplied by its ohms per volt rating is the input impedance of the voltmeter. And you saw that it changed as you changed to different ranges. So which of the following methods measures intermodulation distortion in an SSB transmitter?
Bravo.
Yes, it's the two-tone test. You modulate the transmitter using two audio frequency signals having non-harmonically related frequencies and observe the RF output with a spectrum analyzer. And what technique shows that a square wave is made up of a sine wave and its odd harmonics?
Alpha.
Fourier analysis, yes. And which of the following describes a signal in the time domain?
C?
No.
Guess I missed that one.
So we're in the time domain, we're measuring amplitude on the vertical scale and time on the horizontal scale. I would prefer the answer to be amplitude over time, over a time period, but they say amplitude at different times. So I included this phrase on one of my slides, but I'm not real happy with this question. But okay, amplitude at different times is a way of describing time domain. So what is the benefit of making voltage measurements with a true RMS calculating meter?
Delta.
Yes, RMS can be measured for both sinusoidal and non-sinusoidal signals. And what is the approximate ratio of PEP to average power in an unprocessed single sideband phone signal?
Alpha.
2.5 to 1. And what determines the PEP to average power ratio of an unprocessed single sideband phone signal?
B.
Yeah, your speech, your characteristics of speech. Now, and you can add into the processing, but they say unprocessed. But yeah, speech characteristics is what determines it. And that, ladies and gentlemen, is the end of section 7.1. You have just covered the majority of this chapter with me. Thank you for hanging in there. Let's get up and move around, stretch. We'll take 5 minutes, and then we'll come back and do section 7.2 on receiver performance, which will also make your head explode. But oh, come back, please. 5 minutes. we're back. I hope you got a chance to get your brain cooled down a little bit. And we're going to get right back into it, talking about receivers, one of my favorite topics, receiver performance. And the thing is, there's an old adage, you can't work them if you can't hear them. And the two things that we ask of our receivers are to be sensitive, to be able to pick up weak signals, and then also to be selective, to cut out interference so that we can hear the signals that we want to hear. And some of the older radios, this is a Collins, for example, they're surprisingly good even today. The Collins and the Drake receivers, you'll see them at Hamfests. Why are they still, is there still a market for those? Well, because they're good. They meet the sensitivity and selectivity rules that we want. And the thing is, you can't add a receive linear amplifier like you can with a transmitter to increase its transmitter output power. Well, you can't really do that with a receiver. The receiver's characteristics are kind of cooked in when they're designed. A concept that I want to just review briefly is the concept of the dBm, or the decibels to a milliwatt. In this case, that's our standard. 1 milliwatt across a 50 ohm load for receivers is the equivalent of 0 dBm. That's our reference level, 0 dBm. And then you can have signals that are above that or more than 1 milliwatt, and you can have signals that are lower than that are less than 1 milliwatt. And positive dBm, negative dBm. So if we're looking up, so times 10, which you might remember, 10 dB is 10 times. So times 10 would be 10 milliwatts, or plus 10 dBm would be 10 milliwatts. Plus 20 dBm would be 100 milliwatts. Plus 30 dBm would be 1 watt. 40 dBm, 10 watts. 50 dBm, 100 watts. 60 dBm, 1,000 watts, and then 61.76 dBm is the same as our full legal limit power of 1,500 watts. So these are the plus dBms, power above 0 dBm, or 1 milliwatt across 50 ohms. Going down, well, we have minus 10, so that's a tenth of a milliwatt, minus 20, a hundredth of a milliwatt, minus 30, minus 40, minus 50, until we get down to minus 60, which is 1,000 picowatts of power. You think, well, Gary, that's as low as you can go, isn't it? No. The cell phone industry has a standard of minus 100 dBm, which is the equivalent of 0.1 picowatts, and service must be above that level in order to make your cell phone work. So we actually have receivers that work down to that level. Well, the question is then, Gary, how low can you go? And so the theoretical minimum discernible signal is minus 174 dBm for a 1 hertz bandwidth. Minus 174 dBm per hertz. That's the input of a perfect receiver at room temperature with a 1 hertz bandwidth. That's 4 quintillionth of a milliwatt. Oh my word. Atmospheric noise is much higher than this number. But keep that in mind, that's a reference level, minus 174 dBm. So we're talking about a 1 hertz bandwidth. And so here is what we just talked about, the 174 for 1 hertz. Well, if we were to double that bandwidth, that's the same as times 2 or 3 dB. 6 dB is 4 dB, remember? 10 dB is 10 dB. Well, if you double the bandwidth, it's the same as increasing the noise power by 3 dB. So we started with minus 174, but if we double the bandwidth, it goes to minus 171. Remember, these are minus numbers. So 3 dB, is actually a smaller number, but it's a smaller minus. So this is the minimum discernible signal for a 2 hertz bandwidth. And you might remember the formula, I think it's in the book, for decibels is 10 log to the base 10, one power over the other power, and give you the answer in dB. But also remember that 3 dB is times 2, 6 dB is times 4, 10 dB is times 10. Knowing those, you can get get the answer to most problems you want to work out. So theoretical minimum discernible signal and bandwidth. This is where we started again. Minus 174 at 1 hertz. We took it with a 2 hertz or 3 dB reduction to minus 171. Well, they ask us on the test to consider a 400 hertz CW filter. Okay, so using a calculator, you could do it this way. You could do 10 log 400 over 1, and it'll tell you the answer is 26 dB. Or you can, 400 is 10 times 10, or 100, times 4, 400, 26 dB. So the minimum discernible signal with a 400 hertz bandwidth is minus 174, the base reference, plus 26, minus 148 dBm, minimum discernible signal at a 400 hertz bandwidth. That's pretty darn small, especially when you consider atmospheric noise. If you look on this chart, it has power in dBm, minus dBm here on the vertical scale, and frequency in megahertz on the horizontal scale. Here's minus 148 down here someplace, all right? And these lines are atmospheric noise depending on frequency. So here's the 80 meter band, about 3 megahertz. Here's the 40 meter bands, 7 megahertz. The 20 meter band, 14 megahertz. These are typical atmospheric noise levels. It's greater than receiver noise, even with attenuation added. If we were to add 10 dB of attenuation, this is still greater. So it's the primary noise source of receiver noise is atmospheric noise. And we can look at this chart a little closer here. This is from the Flex users group, and one guy there added the S meter corresponding relationship. So it's not unusual on 80 meters to have, even out in the country, in quiet rural areas, S3 noise level on 80 meters. That's not unusual. That's typical. And in the city, though, it's much higher noise levels, maybe S7, for example. So this is a very interesting chart. Just know that atmospheric noise is going to actually be much higher than anything, the receiver noise that we were talking about there. Now, the receiver or preamp's noise figure is defined as the ratio in dB of the noise generated by the device compared to the theoretical minimum noise. Okay, lower is better. It's useful as a figure of merit for terrestrial systems. A typical low noise UHF preamplifier is going to be less than 2 dB of noise figure. And so the actual receiver's noise figure is the theoretical, plus the noise figure gives you your actual. That's the figure of merit for a receiver. Just to explain some terms that were used in the chapter. So let's have a little game here. Let's play What's the Image Problem? Do you have an image problem? Do I have an image problem? Well, here we're talking about single conversion super heterodyne receivers. And you might remember from the general class that with a single conversion superhet, you have a signal coming in from your antenna, maybe through an RF amplifier, and then it goes to a mixer stage where it's mixed with the local oscillator, and you get the sum and the difference frequencies, and one of those is going to be your IF output, 455 kilohertz typically, and you're going to have a filter that's going to just filter that through. All right, goes to the IF amplifier, demodulated, and on out as audio. That's great, except that the solution, in order to get 455 kilohertz, when you have a local oscillator, there are two possible solutions. If the desired signal you want to receive is below your local oscillator signal by 455 kilohertz, hey, that works. However, if another signal is 455 kilohertz above your local oscillator, that too will come through. That's called an image, or an image frequency. And one way that you can eliminate that is by use of something called a pre-selector. A pre-selector goes in front of the RF amplifier in your radio. It may be built into the radio, or it may be outboard. And it's a tunable circuit that's allowed to sharpen up to try to eliminate or block some of those undesired image or out-of-band interference signals. That's a pre-selector. And some of them are also used with the transceivers. They have RF sensing, so they can go into bypass should they sense transmitted RF coming back to them. That's the single conversion super heterodyne radio. That's where you're going to have image problems. And one thing you can do is add a pre-selector. Well, Gary, okay, how do I find, when I might have an image problem, how do I find the frequencies? Well, what you do is you take the IF frequency times 2, so in this case 455 kilohertz, gives us 910 kilohertz, and then you add 910 to the desired receive frequency, and that'll give you one possible image. Or you subtract 910 from your desired receive frequency, that'll give you another possible image frequency. So if you need to calculate image frequencies, that's a way that you can do it. Now, most ham radio manufacturers have long ago moved away from single conversion receivers, although you'll still see them, like the Radio Shack DX150A. You'll still see those at Hamfest. Those are single conversion. They've moved to what they call double or dual conversion, or even triple conversion radios. And what they do here is you have your RF signal coming in. It goes to a mixer, yes, but the mixer takes it up in a frequency, up to maybe 50 megahertz. Does some filtering there, and it goes to a second mixer. This is the second conversion. And here it's mixed back down to 455 kilohertz, and then the cycle goes on. By using this high frequency for the first IF, it means that there's easier front-end filtering, and it eliminates image frequencies. So signal-to-noise ratio is important to us. We want to have the best signal-to-noise, and we can get that by matching our selectivity, the selectivity of the radio, to the mode that we are receiving. So for radio teletype or digital, 300 hertz is typical, although for FT8 you probably want to have 3000 hertz. For CW, between 200 and 500. Single sideband, up to 2.7 kilohertz. AM, 6 kilohertz. VHF, FM, 15 kilohertz bandwidth. But matching the bandwidth to the mode gives you the best signal-to-noise ratio. And noise, we talked about atmospheric noise earlier. That's one thing that we're trying to eliminate. But there's also something called generated noise. And generated noise can be in a transmitter, or it can be in a receiver. And it can be amplitude or phase noise, or even something called shot noise, which you'll know it when you hear it. It's go pop, 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 pop. That's shot noise. Phase noise is something you more have to see, but it's a kind of a jitter in a signal that you expect to be in a certain spot at a certain time. Well, I like this one better, this graph. So here's a sine wave, but it has phase jitter. Its frequency is slightly varying. Maybe the power supply filtering is not great, or something is going on, and that phase jitter widens the bandwidth of this signal. So if this is in a transmitter, for example, this is the VFO for the transmitter, the signal is going to be wider than it should be. If it's in a receiver, this could be the local oscillator signal. That's going to cause you problems on receive. Phase noise. So here's what you want. You want a single frequency, perfect sine wave. But when you get that fluctuation that we just saw with amplitude and phase, then you get a signal that looks more like this. It's got components on that frequency, but it's got these sidebands going out. That's phase noise. And above and below that center frequency, this is the noise spectrum of that signal. And the spectrum that could be obtained using a spectrum analyzer that shows the noise. And receivers, for example, their local oscillators have been measured. These are some older radios, but these are typical. You can see it's going to cycle through there. Phase noises of one of the sidebands of a local oscillator in these various radios. So it's a Yaesu there, then there's an ICOM, and then I think it adds the SDR 1000. So phase noise is an issue. Phase noise on transmit, like we said, will widen the signal out. And that phase noise is going to be amplified by your power amplifier in the radio and even your linear amplifier after that. So you want a signal as clean as possible. And then receiver phase noise, that local oscillator, you want it to be as pure as possible. I mentioned those Collins and those older Drake radios. Why are they still being sold and purchased? Because they had really low phase noise. The permeability tuned oscillators and the Collins and whatnot, they weren't using direct digital synthesis or phase lock loops or anything like that, and so they're really quiet. A problem with phase noise in a receiver can be called reciprocal mixing or phase noise masking. And what happens, and you may have to look real close here on this one. In fact, I got to put my glasses on. But here we have our local oscillator signal, all right? And here's our desired signal that we want to receive. See it down there? It's not very weak, not very strong. And so the difference between is 455, here down below, 455, all right? That's our IF. But here's a really strong off-channel signal that can mix with our equally strong phase noise over here and can cause interference. It can cause strong beat signals with phase noise. This is reciprocal mixing. Not a good thing. That's why receiver designers try to reduce the phase noise of all of the oscillators in their radios for both transmit and for receive. Some other things that we look at, blocking dynamic range. And this refers to the intermediate frequency amplifiers in a radio. If a radio frequency signal goes up by 1 dB, well, you want the signal in the IF to go up by 1 dB. If it goes up by 6 dB, you want the signal in the IF to go up by 6 dB. But there's going to be a limit. There's going to be a top end of your IF amplifiers, and there's going to be a point when the signal goes up by 2 dB, for example, but the output of the IF amplifiers only goes up by 1 dB. That's compression. And so blocking dynamic range talks about the dynamic range of the amplifiers in the radio. And blocking dynamic range is when there is 1 dB of compression in the receiver's IF amplifiers. That's the blocking dynamic range of that radio receiver. This can be improved because sometimes those signals that are coming in that are strong are off frequency slightly. And if you can add in a super heterodyne radio, dual conversion or triple conversion, a roofing filter. It's after the first mixer, that 50 megahertz IF, and if you put in a roofing filter there, then it can eliminate some of the adjacent channel interference that might get into a blocking compression. And the roofing filter, for example, is added. Here's our coming in of the first mixer. the 50 megahertz IF. Here's where an IF filter might be installed. In this case, it's a 12 kilohertz roofing filter. Then the second mixer, it improves blocking dynamic range by rejecting nearby strong signals. And a radio with a poor dynamic range can easily be desensitized by strong nearby signals. And so that's one thing. It can be the sensitivity can go way down. You can also get cross modulation with interfering signals coming in that impact the signal that you're trying to receive. There's more information here that you can read at your leisure and follow the URLs as well. Another measurement of receiver performance is third order intercept point. And this marks the receiver's performance in the presence of strong RF signals. And it's defined as the point at which two equally strong interfering signals, a pair of signals, generate a third order intermodulation product equal to a desired signal's level. You want this intercept point to be as high as possible, and because the third order product of two in-band signals is also likely to be in-band. So what I want you to remember about third order intercept point, it's a pair of signals. See what I did there? A pair of signals that generates interference equal to the original signal that you're trying to receive. For software-defined radios, we have to be concerned with overload, and one of the things that they've added, this is in the 7300 in one of the iterations, they added something called the IP plus function. That's what they're talking about here, intercept point plus, which allowed the radio to work in the presence of stronger signals. And if you don't know about it already, you probably do. Sherwood Engineering, Rob Sherwood has put together his famous table of receivers or transceivers. And they're rated or sorted based on reciprocal mixing dynamic range, the dynamic range of the radio that can be used in contest conditions. And so take a look. Really, the numbers are different, but the first 20 radios on the list are probably equally as proficient. All right, let's talk about some harmonics here just for a second. We have the fundamental frequency here, and we have then the second harmonic, the third harmonic, the fourth harmonic. So if this is 1 megahertz, then this is going to be 2 megahertz, and this is going to be 3, and this is going to be 4, and this is going to be 5. Those are harmonics. Also, we looked at mixers, remember, and we have outputs from the mixers, the sum of the input frequency and the local oscillator frequency, and the difference, okay? And intermodulation distortion products. You can have third order products, fifth order products, seventh order products. So what the heck are you talking about there, Gary? Well, it has to do with this formula, and on pages 7, 17, and 18, we have this. We want to find some frequencies that would be third order products. And we're looking at this formula. I'm going to put my glasses on again. Up here, if we look at the, we have n times f1 plus m times f2, or n times f1 minus m times f2. If n plus m equals 2, then that's called a second order product. If n plus m is equal to 3, then that is a third order product. And here's the thing. Third order products are what I call the pesky ones. So they're closer into the fundamental frequencies. Here's frequency 1, here's frequency 2. If they intermod, if they generate problems, the third order products are closer in, and in fact the subtractive third order products right here are going to be very close to the fundamental frequencies. So that's why we always say third order products are the ones that we have to be concerned about, because it could be within our IF passband. So third order subtractive products are the ones that we need to be worried about. All right, there is on page 717 a question E4D05. And I'm going to let you read through this at home, but I've tried to highlight here some of the things that we can do to do the calculations. So you're listening on 146.7. When another signal on 146.52 is transmitted, it mixes with a third signal causing interference to the first one. What is that missing signal? Well, you can use these formulas here to calculate what that third frequency could be. And there are two solutions. So you can take that equation, you algebraically convert it, then you take it down to a new equation, you do the calculations, and you find that one of the solutions is 146.34. All right? A second solution uses this formula. You convert it again, it gives down to a new equation, and you go through and you find that it's 146.61. So here are the answers to this question, 146.34 and 146.61. I want you to review and be able to do the formula, but I would not be upset if you memorize the answer to this question. And so 34, the atomic number for selenium, and 61, which I think of 61 asterisk or 61 star. It was a movie that dealt with Roger Maris when he broke Babe Ruth's 60 home run record, but there was an asterisk put by his title because there were 161 games when Babe Ruth was playing in a season, 162 when Roger Maris played. So it always tainted his breaking Babe Ruth's record. Anyway, 34 and 61. 34 and 61. Oh, by the way, in this movie, my brother-in-law from my first marriage, Randy Godwin, played fan number 1. So if you got the movie, go take a look. Fan number 1, that was my brother-in-law. For FM receivers, there's an interesting phenomenon. We say that FM is very discriminating. That's because FM uses a discriminator, and one characteristic of a discriminator is the capture effect. Only the strongest signal will be captured by the discriminator. And a second weaker signal, even if it's on the same frequency, may not be heard. Only the stronger in amplitude of the two signals is heard because of the FM capture effect. All right, I added this slide, and why did I add this slide? Oh yes, for software-defined radios. And so there are various different kinds of SDRs out there, and we have to be concerned with SDR analog to digital converter overload. And Dave talked about this earlier in one of his chapters, but the maximum signal value is controlled by the converter's reference voltage. That sets with the maximum signal. And if you go over that, here's a 7300 with the AVF or overflow indicator, that indicates that it's too strong a signal. So what we're talking about here, and the analog to digital converter could be right at the antenna. That's a direct capture ADC, or it could be at an IF frequency, which is where we see it here. And this analog to digital converter has a reference level, that's the maximum signal level, and then it has a bit depth. 10 bits, for example, remember, was 1,024 steps. This sets the minimum signal that can be received. This sets the maximum signal. So here's another closer look into the ADC. And the reference voltage sets the maximum signal. The smallest resolvable signal is selected by the number of bits in the word that the ADC is using. And then also the number of bits is involved in something called nonlinearity or differential nonlinearity. It has to do with least significant bit errors. It can't resolve things properly. And the dynamic range of an SDR is also the sample width in bits sets the dynamic range of a software-defined radio. So more bits gives you better range and also lower distortion, lower differential nonlinearities. Now, in SDRs, and I actually had to do some research because I hadn't realized this, clock noise is also an issue. Remember we talked about local oscillator noise for analog being a problem? If the clock in an SDR is not pristine, phase noise in the clock signal can mix with strong RF signals in a digital domain and give you spurious reception. So just be aware of that SDR clock noise is something to be considered. All right, here's the scenario. Come back to me for a second, Bruce. So you're with your buddies, you're going to the Ham Fest, but there's so many of you, you had to take 2 cars. So there's a car ahead of you and you're in the second car, and everybody's monitoring the local ham radio repeater, and you hear somebody talking on the repeater from a distance, and then all of a sudden you see the guy in the front pick up the microphone and he's going to talk, and you can see that he's talking, but you can't hear anything. Your radio is quiet. That happens? Yeah, that happens. So that's when you're close in with somebody else, you're convoying to a ham fest, and what happens is when the guy in front of you keys up his transmitter, it desensitizes your radio receiver. It's called desense. It's a reduction in receiver sensitivity caused by strong signals near the receive frequency. So even though he's transmitting on the repeater's input frequency, it's only 600 kilohertz away from you if it's on 2 meters from the receive frequency. That's enough to desense your own radio. So just be aware that this phenomenon occurs. You can improve it by decreasing the bandwidth on the front end. That's one way. And another way is, and it's counterintuitive, you can add attenuation to your receiver. And if you do that, then your receiver will be less desensitized by external signals. It sounds weird, but it's true. All right, ready for some questions? So what is an effect of excessive phase noise in an SDR receiver's master clock oscillator?
B.
Delta, yes, it can combine in the digital domain with strong signals on nearby frequencies to generate interference. Wow. So which of the following receiver circuits can be effective in eliminating interference from strong out-of-band signals?
Alpha.
Yeah, a preselector or a front-end filter? Yes. And what is the term for the suppression of in an FM receiver of one signal by another stronger signal on the same frequency? What is that called?
Alpha.
Not alpha. That's called C, the capture effect of the discriminator. So 2 signals on the same frequency, it's only going to receive the stronger of the 2. What is the noise figure of a receiver?
Delta?
It is delta. It's the ratio in dB of the noise being generated by the receiver to the theoretical minimum noise. And what does a receiver noise floor of minus 174 dBm represent?
Bravo.
Yeah, that's the best that we can do at 1 hertz bandwidth. Perfect receiver at room temperature. And how much does increasing a receiver's bandwidth from 50 to 1000 hertz increase the receiver's noise floor? So you're increasing it by 20. 20 times 50 is 1000.
Delta.
So 10 times would be 10 dB, and then 10 times 2, or 3 dB times 2, 13 dB, yes indeed, 13 dB. And what does the MDS of a receiver represent? I almost said it.
B.
B, the minimum discernible signal. And an SDR receiver is overloaded when input signals exceed what level?
Delta.
Delta, the reference voltage of the ADC, the analog to digital converter. And which of the following choices is a good reason for selecting a high IF for a superheterodyne HF or VHF communications receiver?
Charlie.
You won't have an image problem. Yes, easier for front-end circuitry to eliminate images. And what is an advantage of having a variety of receiver bandwidths from which to select?
Charlie.
Yeah, we're always looking for the best signal-to-noise ratio and minimizing interference. So matching bandwidth to mode bandwidth will do that. So why does input attenuation reduce receiver overload on lower frequency HF bands with little or no impact to signal-to-noise ratio?
Delta.
Delta, yes. Atmospheric noise is always much greater than internally generated noise, even after attenuation on the lower frequency bands. And how does a narrow band roofing filter affect receiver performance?
Charlie.
Yes, it improves the blocking dynamic range by attenuating nearby interference signals. Yep. What is reciprocal mixing?
Delta.
So the local oscillator's phase noise that can mix with a strong signal and come on through to the IF, that's no good. You're trying to receive the weak signal. All right, what is the purpose of the receiver IF shift control? What do you think?
Charlie.
Yeah, you're trying to reduce interference. And what is meant by the blocking dynamic range of a receiver?
Alpha.
Yeah, blocking dynamic range has to do with 1 dB of compression. And which of the following describes problems caused by poor dynamic range in a receiver?
Alpha.
Yeah, okay, you're right. But let's look at some of the others. So oscillator instability and severe audio distortion, we didn't talk anything about that. Poor weak signal reception caused by insufficient local oscillator injection. No, we didn't talk anything about that. That's not true. Oscillator instability requiring frequent retuning and loss of ability. We didn't talk about that. So it's spurious signals caused by cross-modulation and desensing from strong adjacent signals. That's all a factor with a radio that has poor dynamic range. And what transmitter frequencies would create an intermod product signal in a receiver tuned to 146.7 when a nearby station transmits on 146.52? What are the numbers?
A.
Yeah, 3-4, selenium, and 6-1, Roger Maris. So what is the term for the reduction in receiver sensitivity caused by a strong signal near the received frequency?
Charlie.
Yeah, this is the answer that somebody was trying to give it to us before. So yes, desensitization. And which of the following reduces the likelihood of receiver descents? It's counterintuitive.
A.
Alpha.
Yeah, you insert attenuation. So what is the purpose of the preselector in a communications receiver? A preselector is just another filter at the input of a receiver.
And Charlie.
Yeah, to increase the rejection of signals outside the band being received. So what does a third order intercept level of 40 dBm mean with respect to receiver performance? We're talking about intercept point. Think fruit.
The pair.
It's a pair of 40
Delta.
dBm input signals
Delta,
will
Charlie.
theoretically generate a third order intermod product that has the same output as either of the input signals. That's intercept point, third order intercept.
Tricky one.
So why are odd order intermodulation products created within a receiver of particular interest?
Alpha.
Yeah, they're going to be close into the fundamental frequencies, so yeah, they're the pesky ones. Odd order products of the two signals in the band being received are also likely to be within band. So what power level does a receiver minimum discernible signal of minus 100 dBm represent? This is the cell phone guys. Minus 100 dBm is?
Delta.
Yes, delta, a tenth of a picowatt. Holy smokes, that's small. All right, last section, interference and noise. We saw this chart earlier, the atmospheric noise levels and the residential, the rural, and the quiet rural lines that you see up there. Lower is better. Quiet rurals is, if you're going to work HF DX, that's kind of where you want to be. Now, QRN is natural interference. QRM, man-made interference. Well, QRN, atmospheric static, is largely caused by thunderstorms. And so that's going to be the cause of most QRN. I love this website, Blitzortung, which gives you, if you go here to this URL, a map of North America. And it shows you in near real time where thunderstorms and lightning storms are in your area. So QRN, mostly lightning. That's what we're concerned about. Now, QRM could be man-made from some other source. Or are you QRMing yourself? In many cases, we have a lot of noise sources here inside your own home that you need to deal with. And you know, the methods are to use a portable radio, to turn off power to various rooms in your house, see if the noise goes away. Okay, it's in that room. Let's go find it. Could be a little wall wart power supply, for example, that generates RF noise in the HF bands. That can happen. What we're talking about when we're talking about noise, or noise signals in this case, is what we know as common mode. So if we look at signals inside of a coax cable, for example, it's a differential. If it's going positive on one side, it's going to go negative on the other. Or in a coax, for example, if a current is going one way on the center, it's going to go the other way on the shield. Common mode signals are with reference to earth ground. So common mode signals on that same would be signals that might be going from here down to ground, or from here down to ground. Those are known as common mode. And it's a kind of signal transfer from transmitters to wiring, or from a noise source to an antenna system. Common mode. And one of your friends in eliminating common mode, remember, ferrites are your friend. Common mode signals can be blocked by adding inductive reactance on the outside of a cable. And so just by putting these ferrites on there, you can reduce a lot of noise to receive signals, for example. Even on the coax coming into your shack, if you go down to my shack, you'll see I've got ferrites on all of the lines coming from my antennas just to try to block some of the common mode. All right, anybody still got one of these touch control lights? They're notorious for causing radio frequency interference. It sounds like AC hum on an AM receiver. The signal can drift across the HF spectrum. It's usually several kilohertz in width, and it repeats along the IF bands. Touch control lights are notorious. Transmitter intermodulation. This is when you have two transmitters near each other. Think field day for amateur radio, or think a commercial site like this. Transmitters here on top of a mountain like this will interfere with each other. The signal from one transmitter will go to the antenna, be received on another antenna, and back into somebody else's transmitter. And there it will mix with signals and be re-radiated as more garbage. So intermodulation interference comes from mixing of various signals in one of those hodgepodge of antennas and transmitters. And the practical result is that you have off-frequency, unwanted signals heard in addition to the desired signal. The classic for us here in the upstate of South Carolina, if you're in Greenville County, if you are going toward Travelers Rest, you go by Paris Mountain, which has one of those antenna farms like you just saw, and you'll be listening to the 6-1 machine, the Caesar's Head repeater, and all of a sudden you'll hear pager notes coming in. That's all coming from Paris Mountain and from intermod coming from all of that stuff. Some things that can be done: you can use isolators and circulators. They're effective in eliminating transmitter intermodulation. They use ferrites, and a circulator is a 3-port device, well, let's take a look at a picture. So typically 30 dB of isolation between ports with a half a dB of insertion loss. So if you have a transmitter, the idea of the circulator is transmit out from your transmitter into port 1 of the circulator. It'll come out on port 2 and go off to the antenna. Now, if an interfering signal comes in from the antenna, it comes in on port 2 and doesn't go to port 1, but it's carried off to port 3. This is a dummy load. This is a 50 ohm non-inductive high power load here. And so any interfering signals are captured and dissipated as heat. So these are circulators used for reducing transmitter intermodulation at high density transmitter sites. Did you know rust is a semiconductor? Well, it's a non-linear device in any case, and tower corrosion can cause something called passive intermod, where radio frequency signals, like nearby AM radio stations, if their tower gets rusty or your tower gets rusty, the rusty bolt effect takes place, and they're mixed together. The signals get mixed together and causes interference. That's passive intermodulation. All right, a new topic, going in our car now and putzing along, and well, putzing is the right word because the spark system in your car can sometimes do popping noises in your radio, and so there you can have a noise blanker in your radio that fights spark plug noise, impulse noise. There is an issue though with noise blankers on radios. It's a kind of like a pulse squelch system, but you don't want to have it on all the time. because it can remove it removes signals that have a wide bandwidth. That's a good thing, but it can also cause distortion and the widening of received signals. It can make FT8 signals, for example, look like they're being over-deviated when they're not, because the noise blanker's been left on. So just be aware of that. Also in the car, dealing with alternator whine, we always say you can use coaxial capacitors on the alternator leads. Bring your radio power leads directly to the battery. And ferrites. Ferrites are your friend. You can add ferrite beads to the power leads coming to and from the alternator, which can help reduce alternator whine. And if you've got in your house, for example, a big AC motor, and you find that it's generating noise, brute force line filters. Capacitors and inductors in series with the power circuit that will help eliminate noise from motor circuits. There's all sorts of circuits out there, though, that'll cause you interference. Arcing thermostat contacts, if you have an old mercury thermostat, they can generate a lot of noise. Doorbell transformers, they can generate radio frequency interference. And malfunctioning electric signs, especially neon signs, all of those things are the possibility of generating noise interference to your reception. All right, now I'm going to tell on myself. This is the story of how I QRM'd myself, and QRM is not cool. So come back to me just for a second. So when I was getting back into amateur radio, probably back in about 2010, thereabouts, I said I want to get a new radio. I had a Kenwood TS850. It was a great radio, but I just wanted to get something new. And Flex Radio was on the market with their software-defined radios. And I didn't know anything about software-defined radios, and I was fascinated. So I bought a Flex 6500. That's the radio in the upper left. And then they didn't have any control surfaces to control the radios. You had to use software on a PC. So I got a Dell PC at the Hamfest, looked something like this. And I ran Smart SDR software on the PC to control the radio. The problem was, Dave Anderson, K4SV, who's one of our gurus and mentors here, he says, never put your antennas over your house. Never put your antennas over your house. Well, I put my antennas over my ham shack. No good. Anyway, I was picking up a lot of interference from inside my ham shack on the radio. And I could see it here on the display, and I'd look for sources and whatnot. And, yeah, okay. I couldn't find them. Then Flex Radio came out with the Maestro control surface. This is the Maestro, and I thought, ooh, knobs. I want one of those. So I ordered the Maestro, the A model of Maestro, and I put it in my shack and had it controlling my radio. And for whatever reason, at the same time, the interference was there. I could see that interference. But then I had to reboot my computer for some reason. I don't remember why now. And when the computer, that won the Hamfest special, when it turned off, the interference went away. What? My cheap Dell Hamfest computer was actually generating interference. And again, ferrites are your friend. So the moral of the story is that computer power supplies can generate noise and signals in the amateur band. I can attest to it. They're unstable signals at specific frequencies, and common mode filtering on the AC line, in my case, these are toroids, type 31 toroids, with the power cord wrapped through it with multiple turns, that eliminated the radiation of the RF interference. My RF interference went away. So ferrites are your friend. They can eliminate common mode even at the source. Digital signal processing can help you with noise and interference. You can have noise blankers, notch filters, noise reduction. They can be built into the radio, or they can be outboard units. They can operate at the IF frequency, or they can operate at audio frequencies. Just keep in mind, if you're going to use an audio automatic notch filter, which they make them, and it would be used for single sideband. If a carrier comes up nearby frequency, it's going to cause a loud tone in your headphones. Well, if you have an automatic audio notch filter, it eliminates that, so you don't, you have that interfering tone ringing in your headphones. The problem is if you switch over to Morse code, it'll also eliminate all the Morse code signals. You won't hear them. Where'd they go? So what's the difference between a heterodyne and a Morse code signal to your digital signal processing? The answer is nothing. So just be aware that they can cause you trouble if you leave it in the wrong position. All right, last questions. What creates intermodulation interference between two repeaters in close proximity?
Bravo.
Yes, the output signals mix in the final amplifier of one or both transmitters. And which of the following is used to reduce or eliminate intermodulation interference in a repeater caused by a nearby transmitter?
Bravo.
That's a properly terminated circular. That means it's got a dummy load attached at the output of the repeater's transmitter. And what causes intermodulation in an electronic circuit?
Charlie.
It is nonlinear circuits. It could be output power amplifiers. It could be a rusty bolt. It could be anything that's going to have a rectification effect. So what undesirable effect can occur when using a noise blanker? And why we don't leave it on all the time?
Charlie.
It can make FT8 signals look extra wide. Strong signals may be distorted and appear to be causing spurious emissions. Yeah. So which of the following can create intermittent, loud roaring or buzzing AC line interference? Read carefully.
Delta.
Delta.
Yeah, arcing contacts in a thermostat or defective doorbell transformer or malfunctioning sign. Yep, all of those. What could be the cause of local AM broadcast signals combining to generate spurious signals on the medium frequency or HF bands?
Bravo.
It's the rusty bolt effect. It's acting as a non-linear junction, so nearby corroded metal connections are mixing and re-radiating the broadcast signals. Oh, I'm tired. Are you tired? Well, guess what? You made it. The end of Chapter 7. Yay, y'all. I'm so proud of you. Are there any questions before we get out of here tonight? Anything we've covered or anything going on with you? So Dave, next week is the first half of Chapter 8.
It is. Next week, we're going to be talking about modulation, protocols, and modes. We're going to be getting into some digital stuff. And we're going to do this chapter in 2 weeks. So I'll be sending out an email, of course, but usually that's a couple days after our previous class, so I'll just let you know right now. You can read through page 8-11 in the book that covers phase shift keying, or PSK. So to get ready, you can read that part, and that'll be in my email as well. And then the following week, we'll be finishing the modes that are in the chapter, and then get into something called amateur TV, which is kind of a fascinating subject. So that's what's coming up next 2 weeks.
Alrighty, y'all. Thank you for your attention and your patience this evening. Let me say 73, and we will see you all next week. You bet.
Thank you.
Yeah.
That'd be great. Thanks.